Hello everyone, welcome to PW Gulf. So in our series of ultimate recap, today is the turn for the chapter Work, Power and Energy. We'll be revising all the topics of this chapter in today's lecture. So let's see what we'll be covering today. We'll be covering what is work, nature of work, work done by constant force, variable force. Then we'll be doing energy, kinetic energy and potential energy, relation between kinetic energy and momentum. Then we'll go to work energy theorem. We'll be studying conservative and non-conservative forces, relation between a conservative force and potential energy. Then we'll go on equilibrium of a particle, and in the last we'll be doing power. Okay, so all these topics we'll be covering in today's one shot. Okay, let's start with the very first topic, work. So what is work? Work is always done by a force. Whenever we say a work is being done, there must be a force acting which is doing some work. Okay, so we always say work done by tension, work done by gravitational force. Work can be done by any force. Okay, what is the work done? If a force acts on the body and the body displaces in the direction of applied force. Okay, if work is being done, work can be done by a force only and only when a force is acting on the body and the body displaces in the direction of applied force. Okay, work is said to be done whenever a force acts on a body and body moves through some distance in the direction of force. Okay, so for work, first we need necessary conditions for work. These will be: number one, force must act. Okay, work will be done by some force. Force must be acting on the body. Okay, force must be acting on the body, and next there must be a displacement in the direction of applied force. There must be a displacement in the direction of applied force. Okay, there must be a displacement in the direction of applied force, then only work can be done by a force. Now what is the amount of work done? How we define a work done? Okay, so let us start. If constant force is acting, suppose we have a block on which constant force is acting. Okay, on which a constant force is acting. Now this block is displaced by an amount s in this direction. Okay, this block is displaced by an amount s in this direction. Okay, if some F force is acting, let us take it along some angle. Okay, F force is acting and the block is displacing by an amount s. So this will be our s vector, constant force F. F is a constant force. F will be a constant. Okay, a constant force is acting and the particle displaced in this direction, making an angle theta with the force. Okay, making an angle theta with the force. Then what will be my work done? Work done by the force will be F dot S. Okay, work done by the force will be F dot S. If theta is the angle between the force, then F dot S will become Fs cos theta. So work done is given by Fs cos theta. Okay, if we have a constant force F acting on a particle which displaces it by amount S, and theta is the angle between the force and displacement, so work done will be given by F dot S, which is equal to Fs cos theta. Okay, this will be the work done by the F force acting on the particle. Okay, so this is how we define for the constant force. Now see, what will be a SI unit of the work done? SI unit of work done will be joule. Okay, SI unit of work done is joule, and work is a scalar quantity. Okay, work is a scalar quantity. Why scalar? Because it is dot product. Okay, it is dot product of F vector and S vector. After dot we get a scalar, so work is a scalar quantity. Now let us see nature of work done. Nature of work done. Now first case, if theta is greater than or equal to 0 degree but less than 90 degree. Okay, if theta is an acute angle, it is less than 90 but greater or equal to then 0, then cos theta will be a positive value. Cos theta will be a positive number, so work done will be positive. Okay, work done will be positive when theta is less than 90 degree, like this. Second case, when theta is equal to 90 degree. When theta is equal to 90 degree, cos theta will become 0. Cos theta will become cos 90 degree, which is 0. So work done will be 0. Okay, work done will be 0. Work done will be 0 when force is perpendicular to the displacement. Okay, if this is our displacement, this is our force making an angle of 90 degrees with the displacement. Third, when theta is greater than 90 degree. Okay, when theta is greater than, oh, I wrote opposite. When theta is greater than 90 degree but less than or equal to 180 degree, cos theta in such a case is a negative value, so work done will also be a negative value. Okay, work done will be negative. Work done is negative when theta is an obtuse angle, like this. This is my displacement, this is my force applied. This theta is greater than 90 but less than or equal to 180 degree, then my work done will be a negative. For acute angle we have positive work. For theta is equal to 0 we have 0. For theta is equal to 90 degree we have 0 work. For theta is equal to, or for theta greater than 90 and less than or equal to 180, that is obtuse angle, work done will be negative. Okay, so this is the case. Now let us see 0 work done. Okay, conditions for 0 work done. How can we have, in which cases we can have 0 work being done by a force? Okay, now see, first case, if F is equal to 0. If F is equal to 0, then work done will be 0. Second case, if S is equal to 0, then also work done will be 0. And third case, if cos theta, second case, if theta is equal to 90 degree, cos theta will be 0, then also work done will be 0. So we have 3 cases in work done will be 0. First case, no force is applied. Okay, no net resultant force. Okay, or we can say no force is applied. or if sum of all the forces on a body becomes 0, net resultant of all the forces on a body becomes 0, then we will say that total work done by all the forces will be 0. Okay, and in next case, force is applied, displacement is 0. Okay, displacement is 0. We applied some force, but there is no displacement of the object. Example, apply the force on a wall. Okay, wall doesn't move, so displacement is 0. You still applied a force. And then third case, force is perpendicular to displacement. Force is perpendicular to displacement. Now there are so many examples of this third part. When we say work done by centripetal force will always be 0. Okay, work done by tension, when we in a pendulum, work done by tension will be 0. If you hold some object and start moving horizontally, if you hold some object on your head, you lift some object and start moving horizontally, then also work done will be 0. Okay, object is moving horizontally, work done by mg will be 0. There are so many examples of this third case. Okay, now let us move to work done by a variable force. Whenever we have a variable force, see, variable force will have a changing value. Okay, at every point there will be a changing value of f. Now if at every x my f is changing, let us take a very small interval of the, suppose this side we have. Now if I take a very small interval, if I take a very small interval such that this interval is infinitesimally small, okay, it is infinitesimally small, I have made a large interval. When we divide this into infinite, this dx will be very small. Okay, this dx will be very small. If this dx will be very small, then this force is almost a constant. So work done in this small displacement dx will be given by f dx, force f, and dx displacement. So total work done will be integration of all the small work done. Now what we did is we divided our displacement into very small intervals of displacement. Okay, so we'll calculate the work done for each small displacement and then we'll be adding them. So total work done will be integration of dw. So total work done will be integration of f dx. Okay, integration of f dx. Limit of x will go from x1 to x2, from where till where you want to find the work done. Okay, from where till where you want to find the work done, that will go on the limit. Now see, if we have a plot between f and x, okay, if there is a plot between displacement and force, there is a plot between displacement and force, and I want to find this area. I want to find this area. This area will be given by integration of y dx, that is integration of f dx from x1 to x2, from where till where you want to find the area. Now see, what is this? This is work done only from x1 to x2. So area under force displacement graph. Okay, area under force displacement graph gives the work done by the force. Area under force displacement graph gives the work done by the force. Okay, So this is important statement. Area under force displacement curve will give us the work done by the force. Let's move forward. Work done in rectangular components. Okay. Now force is a vector. If we have force as Fx I cap plus Fy j cap plus Fz k cap, and displacement as Sx I cap plus Sy j cap plus Sz k cap. Okay. A force is acting Fx I cap plus Fy j cap plus Fz k cap on a body, and displacement is Sx I cap, Sy j cap plus Sz k cap. Now what will be my work done? Work done will be F dot S vector. Now take the dot product of these two vectors. I dot I, it will become Fx into Sx, then J dot J, Fy into Sy, then Fz into Sz. Okay. So this will be the work done in terms of rectangular components. Whenever we are given in vector form, force and displacement in vector form, then we can find work done by using the dot product. Okay. So next is energy. What is energy? Whenever we are doing work, we in our body there is a capacity to do work. Okay. We are able to do work when we have some energy, when we possess some energy. Okay. So capability or capacity or ability of a body to do some work is called energy. Okay. So energy is defined as capacity or ability to do work. Capacity or ability to do work. The energy contained in a body will define us that how much ability or how much work this body can perform. Okay. How much work this body can perform in the future. So energy of a body is measured by the amount of work the body can perform. Okay. Now there are different types of energy. There are various types of energy. What types of energy we can have? We can have mechanical energy. Okay. Mechanical energy, thermal energy, sound energy, nuclear energy, light energy, chemical energy. Okay. We have various numerous types of energy. Okay. Chemical energy, solar energy, wind energy, etc., etc. Okay. We have many types of energy. What is energy? Energy is a scalar quantity. Okay. Energy is a scalar quantity. Now SI unit of energy will be same. It will be joules. Okay. What is energy? Energy tells us how much capacity is present in a body to perform some work. So energy and work are equivalent. Okay. So SI unit of energy is joules. SI unit of energy is joules. If we say CGS unit will be erg. Okay. CGS unit is erg. Now 1 joule is equal to 10 raised to the power 7 erg. Okay. 1 joule is equal to 10 raised to the power 7 erg. 1 joule is equal to 10 raised to the power 7 erg. This is the conversion between SI and CGS unit. Now if we want to find the dimensional formula, it will be mL2T minus 2. Okay. Same, energy and work have the same dimensions. Energy and work have the same dimensions. Okay, so this is energy. Now we'll be studying two types of energy, or we'll be studying mechanical energy, which is further of two types: kinetic energy and potential energy. So we'll be studying kinetic and potential, that is mechanical energy. Now if we have a body of mass m, okay, if we have a body of mass m and this is moving with speed v, this body is moving with speed v, then it possesses some energy, okay, which due to its motion, that is called kinetic energy. Okay, the energy possessed by a body by virtue of its motion is called kinetic energy. Now what is the formula for kinetic energy? If we have a body of mass m moving with v speed, then kinetic energy possessed by the body will be half mv square. Okay, kinetic energy possessed by the body will be half mv square. So kinetic energy is directly proportional to mass and directly proportional to square of the velocity. Okay, now kinetic energy can never be negative. Okay, kinetic energy can never be negative. It is always positive. Kinetic energy can never be negative, it is always positive. Mass can never be negative, velocity square, okay, speed square, square of a number can't be negative. So kinetic energy can never be negative, it is always a positive number. It is also a scalar, energy is a scalar, so every type of energy will be scalar. Same unit joule, because it is just type of energy only. Okay, same unit joule, same dimensional formula, ml2 t minus 2. This is our kinetic energy. Let's do the relation between momentum and kinetic energy. Now P is equal to mv and kinetic energy is equal to half mv square. Now calculate the value of v from here. We can write v as P by m. Substitute in this expression, it will become half m into P by m whole square, P by m whole square. So it will become half m into P square by m square. M and m gets cancelled out, so it will become P square by 2m. Okay, it will become P square by 2m. This is the relation between kinetic energy and momentum. We can also write it as P square will be equal to 2 times the kinetic energy, or P is equal to under root of 2m into kinetic energy. Okay, under root of 2m into kinetic energy. Okay, so this is the relation between kinetic energy and momentum. Now work energy theorem. So work energy theorem is a relation which relates work done by force with the kinetic energy. Okay, so what work energy says that the work done by the net force acting on a body, okay, work done by the net force acting on a body is equal to change produced in the kinetic energy of that body. So work done by all forces is equal to change in kinetic energy of the body. Here in all forces we will include work done by conservative force plus work done by non-conservative force plus work done by pseudo force. Okay, so all types of forces, whether it is conservative, non-conservative, pseudo force, all types of forces, work done will be equal to change in kinetic energy. Okay, change in kinetic energy, all the forces, whether they are conservative, they are non-conservative, or they are pseudo force, all types of forces, work done will be equal to change in kinetic energy. This is the work energy theorem. This is the work energy theorem. Now let us see potential energy. What is potential energy? Whenever we are placed in the space, okay, whenever we are placed in the space, whether we are standing on the floor or we are standing on some height, okay, we have different positions or orientations in space, okay. You have a bow which is unstretched, then you have a bow whose string is stretched. These are two different orientations. The energy we get from the orientation of the body or its position in the space is called potential energy, okay. The energy possessed by a body by virtue of its position in a field of force or by its configuration in a space is called potential energy, okay. It is called potential energy. Now potential energy, example of potential energy can be gravitational potential energy, okay. Gravitational potential energy. Gravitational potential energy comes due to position in the force field of Earth's gravitational force, okay. Gravitational potential energy. Elastic potential energy. Where can we get elastic potential energy? In a spring or stretched string. Then we have elastic potential energy, etc. Okay, then we have electrostatic potential energy, okay. So these are types of potential energy or examples. When we place an object mg at some h height, it will possess some gravitational potential energy. If we stretch a spring or compress a spring, if we stretch a string of the bow and arrow system, okay, and if we then we release it, the potential energy in the string is getting converted into the kinetic energy of arrow, okay. So there are types of potential energy: elastic potential energy, gravitational potential energy, electrostatic potential energy. All these are types of potential energy. Now what is gravitational potential energy? How we place a body in the gravitational force of Earth is by due to its position in this gravitational force field of Earth is it possesses some energy, okay. That energy is called gravitational potential energy. The energy which is possessed due to its position in the gravitational force field of the Earth, okay. So energy possessed by virtue of its position above the surface of Earth, okay. So if this is my surface of Earth and a body is placed at some h height above the surface of Earth and m is the mass of the body, then gravitational potential energy will be equal to mgh, okay. So mg into h will be the work done in displacing this particle from here to here. This will be stored as potential energy in the body, okay. Now there is no absolute potential energy. We choose this as the reference level of potential energy. We always choose some reference level of the potential energy, then above it or below it we will define it as mgh, okay. If it is below h height, it will be minus mgh. There is always change in potential energy. There is no absolute potential energy, okay. For potential energy we have to define some reference, then we measure the change in potential energy, okay. So we have a body of mass m, and in this we considered that h is much less than r, such that g is a constant, okay. Such that mgh, g is a constant. This is a gravitational potential energy mgh. So if we have a reference level of 0, any particle above the reference level at some height h will have a potential energy mgh, and if it is below h height, it will be minus mgh, okay. We always have change in potential energy. There is no absolute potential energy. Now let's move to conservative and non-conservative force. What are conservative force and what are non-conservative force? Conservative force are those forces under which if we do some work along three different paths or many different paths, the work done does not depend on the path which is being followed. Okay, it is independent of the path followed. It only depends on the initial and final position of the object. Okay, if we have some force is acting, okay, or some force is present in this force field, and we are displacing any particle from A to B along three different paths. Okay, we are displacing a particle from A to B along three different paths. Okay, along three different paths, then work done in going from A to B along path 1 is equal to work done in going from A to B along path 2 is equal to work done in going from A to B along path 3. Okay, if work done along each path is same, then F is a conservative force. Okay, so for a conservative force, work done doesn't depend on the path followed. It is independent of the path followed. It only depends on the endpoints, initial and final position. Okay, example of conservative force will be gravitational force, electrostatic force, electrostatic force, all these are conservative forces. Okay, all electromagnetic force, all these are conservative forces. Now what is a non-conservative force? Work done depends on the path which is being followed. Okay, work done depends on the path which is being followed. So if we displace a particle along three different paths from the same points A to B, then work done in going from A to B along path 1 is not equal to work done in going from A to B along path 2 is not equal to work done in going from A to B along path 3, then such a force is called conservative force. Okay, example of conservative force are always dissipative forces, that is frictional force, viscous drag, air resistance, all these are non-conservative forces. Okay, it depends on the path along which the object is moving. That force is called conservative force. Okay, that force is called conservative force. Now work done by a conservative force in a closed loop, work done by a conservative force in a closed loop will be 0, because it depends on the initial and final position. So if initial and final position are same, then work done will be 0. You go from A and come back to A, so work done along the conservative force, okay, that is integration of F ds will be 0 along a closed loop, where F is a conservative force. This is only possible if F is a conservative force. Next property we have that work done by a conservative force is equal to negative of change in potential energy, okay, is equal to negative of change in potential energy, okay. Work done by a conservative force is equal to minus delta U, okay, negative of change in the potential energy, okay. So these are properties of conservative force. Now let us move to potential energy in relation to conservative force. Now we just saw that work done by a conservative force is equal to negative of change in potential energy. Now if we do a small work done, okay, work done is equal to minus delta U. If a small work is done, then there will be a small change in potential energy. dW is equal to minus delta minus du, okay. Now what is dW? We can write it as F dx or F ds. So this will be equal to minus du. So from here we will get that F is equal to minus of du by dx, okay. F is equal to minus of du by dx. This is a relation between conservative force and potential energy. Potential energy is always defined for a conservative force only. There is no potential energy for a non-conservative force, okay. So F is equal to minus du by dx. This is the relation between my conservative force and potential energy. Now law of conservation of energy. Now what is law of conservation of energy? It is says that energy can neither be created nor be destroyed. It can only be converted from one form to another, okay. Energy can neither be created, it can never be destroyed. We just convert it from one form to another. Or if we have an isolated system, okay, if we have an isolated system, then its total energy remains constant, okay. So total energy is always a constant. Total energy is always a constant for an isolated system. We can never create energy, we can never destroy energy, we just convert it from one form to another. Suppose we switch on a torch, okay. Suppose we switch on a torch, what will happen? There is chemical energy stored in the batteries, okay. There is chemical energy stored in the battery which gets converted to electrical energy, okay, which gets converted into electrical energy, which makes charges move in the form of current. Then this electrical energy is used to light the bulb of the torch, that is it is converted into light energy, okay, that is it is converted into light energy. Now as the bulb glows, bulb gets heated up, so this is further converted into heat energy, okay. This is further converted into heat energy. There are many similar processes where we can see this conversion of energy from one form to another, okay. This is law of conservation of energy. Now what is law of conservation of mechanical energy? Law of conservation of mechanical energy says that if only conservative forces are doing work, okay, if only conservative forces are doing work, then the mechanical energy of the system will be conserved. Now what is mechanical energy? Mechanical energy is kinetic energy plus potential energy. Mechanical energy is kinetic energy plus potential energy. Mechanical energy is kinetic energy plus potential energy. If only conservative forces are doing work, okay, if only conservative forces are doing work, then work done by conservative forces will be equal to change in kinetic energy by work energy theorem. Okay, by work energy theorem, work done by all the forces is equal to change in kinetic energy. Only conservative forces are present, so conservative forces, work done by conservative forces will be equal to change in kinetic energy. Also we know that we have work done by conservative forces is equal to negative of change in potential energy. So this will be equal to half m v square minus half m u square. Now rearrange the terms. Okay, now rearrange the terms. What we will have? U initial plus half m u square will be equal to u final plus half m v square. Okay, so what is this? This is initial potential energy, this is initial kinetic, this is final potential plus final kinetic. So what we get is initial potential plus initial kinetic is equal to final potential plus final kinetic. So mechanical energy initial, okay, potential plus kinetic energy initially is equal to potential plus kinetic energy finally. So mechanical energy initial is equal to mechanical energy final. This is law of conservation of mechanical energy. Conservation of mechanical energy is only and only valid if we have conservative forces only. Okay, so it states that only if conservative forces are doing work on a body, then its total mechanical energy remains constant. Okay, total mechanical energy will be a constant. Now let us study equilibrium. Now what is equilibrium? When net force on the particle will be 0. Okay, when net force on the particle will be 0, that is the condition for our equilibrium. What is force? Force can be written as minus du by dx is equal to 0, which implies condition for equilibrium will be du by dx is equal to 0. Okay, condition for equilibrium is du by dx is equal to 0. So if we have a curve between u and x, okay, if we have a curve between u and x, where is my du by dx 0? At the maxima and minima. Okay, where is my du by dx 0? At maxima and minima. It means slope of ux will be 0. Okay, so how to find? This is the condition for equilibrium. Okay, this is the condition for equilibrium. When is a body said to be in equilibrium? Whenever we have du by dx, that is slope is equal to 0. Where is slope 0? It will be equal to 0 at the maxima and minima points. Now we have to check whether it will be a stable equilibrium or an unstable equilibrium. Let's check whether it will be a stable equilibrium or unstable equilibrium. First case, if d square u by dx square is greater than 0, okay, or d square u by dx square, d square u by dx square is positive. Okay, it is positive. If d square u is positive number, then what we have over here? We have minima over here. Whenever we have minima, this will be the condition for stable equilibrium. Okay, this will be the condition for stable equilibrium. whenever we have minima of potential energy. Okay, so whenever we have minima of potential energy, forces on disturbing the particle, forces will act in a manner such that they will bring the particle back to its equilibrium position. Okay, it will try to regain its equilibrium position. That's why it is called stable equilibrium. Okay, that's why it is called stable equilibrium. Second case, when d square u by dx square is less than 0, or d square u by dx square, it is negative. Okay, whenever we have d square u by dx square as negative number, what will happen? What will be formed over here? Maximum of potential energy. Okay, maximum of potential energy is formed. So wherever we have maximum of potential energy, it will be unstable equilibrium. It will be unstable equilibrium because forces on disturbing the particle, the forces acting on the particle will be such that it will take the particle away from the equilibrium position. That's why it is called unstable equilibrium. Okay, that's why it is called unstable equilibrium. Now let's do the third case also. If d square u by dx square is equal to 0, then this is called neutral equilibrium. Okay, its point of inflection, it's called neutral equilibrium. The new position will also be in position of equilibrium. Okay, new position will also be a position of equilibrium only. That's why it is called neutral equilibrium. So condition for equilibrium is du by dx is equal to 0. Condition for stable equilibrium is a minimum of potential energy will be formed. Condition for unstable will be maximum of potential energy, and condition for neutral equilibrium will be that its point of inflection d square u by dx square will also be 0. Okay, new position, the particles on disturbing the particle bends from another position which is also a position of equilibrium. Okay, so this is all about equilibrium. Let's move ahead to potential energy of a spring. Potential energy of a spring. So if we have a body which is connected to a spring, if we have a body which is connected to a spring of mass m, then if we apply some force on this spring, then it will elongate. What will happen? It will stretch. Now if x is the displacement, okay, x is the displacement on of the spring of the block, displacement of the block or elongation in the spring, then spring will apply a force Fs on the block to regain. Spring will apply some force Fs on the block to regain its initial position. Now we know that by Hooke's law, this Fs is directly proportional to minus x, and this Fs is equal to minus kx. Okay, this Fs is equal to minus kx. Negative sign shows that it is opposite to displacement. Okay, negative sign shows that it is opposite to displacement. It is opposite to displacement. If we elongate the spring, force will act towards the spring to regain its original position. If we compress the spring, force will act away from the spring to elongate and regain its original position. Okay, so Fs will be equal to minus kx. Now if we are work done by spring force, work done by spring force, what will happen? If we are disturbing the spring from its equilibrium position to a elongation x. Okay, so what we have a spring in its natural length, and we applied some force and we elongated the spring. Okay, we applied some force and we elongated the spring by a displacement x. Now earlier the spring was at a position of x is equal to 0. Now the spring is at a position x is equal to x. Okay, so work done by spring force will be equal to integration of f dx. Okay, integration of fs dx, sorry, fs dx. Spring force will act inwards. Spring force will be acting inwards. When we apply some force F outwards, then spring force will be acting inwards. Okay, so spring force will be acting in this direction. Okay, this is Fs and we applied a force F. Now if we applied and we are moving it slowly such that there is no acceleration, what will happen? Fs is acting inwards, Fs are outwards. So work done by spring force. How much is my value of spring force? Minus kx dx. Limit of x will go from x is equal to 0 to x is equal to x. We displaced it from 0 to x. So work done by spring force will be minus k will come out as common. Integration of x will be x square by 2, limit 0 to x. So work done by spring force will be minus k by 2 into x square minus 0 square. Work done by spring force is minus half k x square. Okay, work done by spring force is minus half k x square. Now we know that work done by conservative force is equal to change in potential energy. So change in potential energy will be half kx square. Okay, change in potential energy will be half kx square. This is the potential energy of spring. This is the potential energy of a spring. So potential energy of a spring is half kx square, where x is my elongation or compression in the spring and k is a spring constant. Okay, k is the spring constant, x is my elongation or compression in the spring. Now if we go from x1 to x2, okay, if we go from x1 to x2, then change in potential energy will be equal to half k x2 square minus x1 square. Limit will go from x1 to x2. So change in kinetic potential energy will be half k x2 square minus x1 square. So from here we see that it only depends on x initial and x final, not on the path followed. Not on the path followed. Okay, work done by spring force only depends on x1 and x2. It doesn't depend on the path followed. So spring force is a conservative force. Okay, spring force is a conservative force. Spring force is a conservative force. Next, work done in a closed path. Okay, work done in a closed path, it will be equal to minus half k x square minus x square. You go from x square and come back to x square, it will be 0. Okay, work done along a closed path by spring force is 0. So spring force is a conservative force. Okay, spring force is a conservative force. potential energy of spring is half kx square. Okay, it is half kx square. Now let us see power. What is power? Suppose A is also doing some work, B is also doing some work. Okay, A is lifting some object, he is doing some work. B is also lifting the object to the same height. Okay, we have two boys. Okay, we have two persons or two boys who are lifting this object to the same height h. Okay, who are lifting the same object m mass to the same height. Okay, they are lifting the m mass to the same height h a b. The time taken by A is 5 seconds. Okay, time taken by B is 10 seconds. Time taken by A is 5 seconds. Time taken by B is 10 seconds. Both are doing the same work, mgh. Work done by A. Work done by A will be mgh. Work done by B, this will also be mgh. But can I know who is having more power? Okay, if I have the ability to do the same work in lesser time, am I more powerful? Yes or no? See, that is power, rate at which the work is being done. Okay, rate of doing work. Both are doing the same work, but one is doing it in 5 seconds, other is taking 10 seconds to do the same work. So the rate at which work is being done, how much work is being done in how much time? Okay, so the rate at which work is being done is called power. Okay, so power is equal to work done by time taken. Okay, power is equal to work done by time taken, or we can also write it in the form of energy consumed or energy delivered by time taken. Okay, because work and energy are related, we can also relate it by energy by time. So if we write P average, average power is total work done divided by the total time taken. Okay, average power will be total work done divided by the total time taken. Now what is power? Power is a scalar quantity. Okay, power is a scalar quantity. Okay, power is a scalar quantity. Now SI unit of power, it is watt. SI unit of power is watt. Now we use some commercial unit. Commercial unit of power, commercial unit of power is 1 kilowatt, which is equal to 10 raised to the power 3 watts. This is a commercial unit of power. And next is horsepower. Okay, horsepower is also a commercial unit of power. 1 horsepower, 1 HP is equal to 746 watt. Okay, 1 horsepower is equal to 746 watt. This is the commercial unit of power. Now dimensions. Dimensions of power will be work divided by time. So ml2 t minus 3. Okay, ml2 t minus 3. This will be my dimensions of work done. Work done is a scalar quantity. Okay, it is a also work done is a scalar quantity. So power will also be a scalar quantity. Now average power is total work done or total energy consumed or total energy delivered per unit time. If we want to see instantaneous power, okay, if we want to see instantaneous power, then we have to now see if work is being done at some time dependent function. Okay, work is a time dependent function. then can we take a very infinitely small interval of time such that in this interval of time my work done is dw. So power will be dw by dt. Dt is the infinitesimally small time interval in which we did a work of dw. So instantaneous power will be dw by dt. Okay, dw by dt. Now let us see one more formula for instantaneous power. First, if we see, we have work time graph. Okay, if we have work time graph, then what will happen? Slope of this graph, slope of work time graph will be equal to dw by dt, which is equal to power. Okay, slope of work time graph will give us power. Now if a force F is acting and particle is moving with constant velocity. Okay, particle is moving with constant velocity v, constant velocity v vector. Okay, then what will be my power? Power will be work by time. What will be my work? Work will be F dot ds divided by time. Let us take instantaneous power. So it will be P is equal to dw by dt. Now some F force is acting on the particle. So dw will be F dot ds divided by dt. Okay, small work done will be F dot ds, where ds is the small interval, a small displacement done in the small time interval dt. Okay, so from here we will get power is equal to F dot ds by dt. Now what is ds by dt? ds by dt is the rate of change of velocity, rate of change of displacement, which is velocity. Okay, so from here power will be equal to F dot v. Okay, from here power will be equal to F dot v. Power is the dot product of force and velocity vector. Okay, power is the dot product of force and velocity vector. Okay, power is equal to F dot v. So this is all about the chapter work, power and energy. I hope this session was helpful to you and you really enjoyed watching it. So keep studying, keep rocking. All the very best. Take care. Goodbye.